Hello students! Our topic today is energy, energia in Finnish. Energy is a slippery concept. It is all around us and everybody knows about it, but many find it very hard to describe. Can you define the word energy? Can you give examples of how you use energy every day? How does the availability of usable energy affect your quality of life?
Energy has become one of the most important factors in our society. An understanding of the terms energy, work, and radiation is necessary not only in the study of physics, but in the total context of our highly technology-based world. Energy is a fundamental concept of physics. Energy is responsible for making everything happen. It causes all changes in the universe. The energy of an object is its capability of producing a force that can do work, as well as its capability of transferring heat. Whenever a system has energy being transferred into or out of it, it can be of two forms, either in the form of heat or in the form of work. Energy has the capacity to do work, and work is the transferring or transforming of energy. Work, too, is motion against an opposing force. So, work is done when a force is exerted to move something over a distance against opposition, such as when a box is moved against a frictional force or lifted against gravity. A raised weight has more energy than one on the ground, because the former has a greater capacity to do work. It can do work as it falls to the level of the lower weight. Let's think about the molecular nature of work. Whenever we think of work, we can always think it in terms of uniform motion of some kind. Mechanical work means that atoms are pushed in the same direction against an opposing force. When a weight is raised, all the atoms of the weight move in unison in the same direction. Electrical work corresponds to electrons being pushed in the same direction through a circuit, and so on. Next, let's consider the molecular nature of heat. Lamp. Heat is the kinetic energy of the chaotic motion of particles interacting with each other. A fuel burning, for example, generates disorderly molecular motion in its vicinity. Work can be completely converted into heat by friction, for example. However, heat can only partially be converted back into work. Therefore, heat is low-quality energy and work is high-quality energy. In general, energy is defined as the ability to do work or to produce heat. Think of work and heat as ways that objects exchange energy. The unit used to report energy, and therefore both work and heat, is the Joule, Joule in Finnish, abbreviated with a capital J. 1 joule is equal to the amount of work done in applying a force of 1 Newton through a distance of 1 meter in the direction of the force applied. Therefore, 1 joule equals 1 Newton times meter. You might remember that 1 Newton is the force needed to accelerate 1 kilogram of mass at the rate of 1 meter per second squared, so 1 joule is equal to 1 kilogram times meter squared per second squared. A joule is quite a small unit of energy, so energy is commonly expressed in kilojoules. 1 kilojoule is equal to 1000 joules. The Joule is named after James Prescott Joule, who was the first person to prove that heat is a form of energy. Joule established a numerical relationship between heat and mechanical work. Energy occurs in many forms that can be categorized in two main classes: kinetic energy and potential energy. Kinetic energy is the energy of an object or a system's particles in motion. Potential energy is stored energy. Potential energy can be converted to kinetic energy and vice versa. Kinetic energy, kineettinen energia, means something is moving and it is happening right now. When you start pushing or pulling an object with a constant force, it starts to move if the force you exert is greater than the net forces resisting you, such as friction and gravity. And if the object starts to move at some speed, it will acquire kinetic mechanical energy, kineettistä mekaanista energiaa. We have already discussed heat. Heat is the thermal energy that flows between two objects that are in contact if those objects are at different temperatures. Thermal energy is an example of kinetic energy as it is due to the motion of particles. Potential energy, potentiaalienergia, has the potential to do work, but it is not actively doing work. When the position, arrangement, or state of the object changes, the stored energy will be released as kinetic energy. An example of potential energy is the elastic energy contained in a compressed spring. It is not doing work, but it has the potential to do so. If you release the spring, the potential energy is converted into kinetic energy. Chemical energy is the energy associated with the relative positions of electrons and nuclei in atoms and molecules. Chemical energy is also a form of potential energy. Some chemical compounds, such as the methane in natural gas, are like compressed spring. They contain potential energy that can be released by a chemical reaction. Energy stored in field can usually be regarded as potential energy. Field is an area of space in which a force has an effect on matter. Examples include magnetic, electric, and gravitational fields. Everyday expressions such as energy production contradict the energy conservation law, energiansäilymislaki, which asserts that energy cannot be created or destroyed. It can only be converted between different forms. People struggled for centuries to create energy from nothing, wishing they could produce work and wealth endlessly. Despite strenuous efforts, they failed without exception. We know now that just as matter is conserved, being neither created nor destroyed, so energy too is conserved. It may be converted from one form to another. And this is how we harness energy to do useful work. But that energy is never actually spent. Energy cannot be made or spent, but it can be moved from place to place. Energy can be exchanged between a system and its surroundings as work or as heat. The law of conservation of energy was first proposed and tested by Émilie du Châtelet. She derived a principle of energy conservation from the fundamental principles of Newton's mechanics. But why is energy conserved? Mathematician Emmy Noether gave us the answer. She established a mathematical link between two important concepts in physics: conservation laws and symmetries. Symmetry means that the properties of particles remains unchanged under some transformation. Noether's theorem states that for every differentiable symmetry there must exist some physical quantity that is itself conserved, meaning that it does not change with time. Space translation symmetry gives conservation of momentum, rotation symmetry gives conservation of angular momentum, and so on. Symmetry with respect to time shift gives rise to the law of conservation of energy. Time translation symmetry means it does not make a difference at what time you start an experiment. The results will be the same. This symmetry in time corresponds to a conservation in energy. The certainty of energy conservation is very important in physics. The total amount of energy is constant, but energy travels in the universe. Energy often gets transferred through a wave, aalto. Waves carry energy in diverse ways. Some waves, such as sea waves and sound waves, physically move the particles of whatever medium they are traveling through. This does not mean the particles are moving far with the wave. The particles only oscillate about a fixed equilibrium point, which means they move back and forth in a regular repeating way. This oscillating pattern carries energy from one place to another, so wave is like a disturbance that transfers energy. It starts with an applied force that temporarily displaces particles. These displaced particles push or pull on adjacent particles, setting them in motion. These kind of waves come in two types. Both types of waves transfer energy but not mass. Transverse waves cause the medium to move perpendicular to the direction of the wave. Longitudinal waves create vibrations that move through the medium in a parallel direction the waves are traveling. In other words, a longitudinal wave consists of multiple compressions and rarefactions in the same direction as the wave moves. Waves have three primary characteristics: wavelength, frequency, and speed. Wavelength, symbolized by Greek letter lambda, is the distance from the start of one wave cycle to the start of the next. For example, the distance between two consecutive peaks. The number of waves that pass a fixed point in a given amount of time is wave frequency. Frequency is expressed in units of hertz, which is equivalent to 1 per second. The shorter the wavelength, the higher the frequency. Electromagnetic radiation, sähkömagneettien säteily, consists of transverse waves of energy moving at the speed of light. An accelerating charged particle produces an electromagnetic wave, which consists of oscillating electric and magnetic field. In electromagnetic spectrum, sähkömagneettisessa spektrissä, the types of rays are arranged based on their wavelength and their frequency. The higher the frequency, the greater the energy. You cannot feel a radio wave, but infrared waves are strong enough to warm your skin. Ultraviolet rays can give you a sunburn, and enough gamma rays would vaporize your cells. As you can see from this picture, visible light is only a tiny slice of the electromagnetic spectrum. The energy also relates to the color we see. Blue light is composed of faster oscillating waves than red light. Without reflection of light off a surface, we would not be able to see objects. Color is an interpretation of the wavelength of light being seen. Sunlight is pretty much white, but it is made up of all the colors of the spectrum. It is light, valo, that carries the sun's energy across space and makes the Earth warm enough for life to exist. Light is considered to have wave-particle duality. It sometimes behaves like a wave and sometimes like a particle. Electromagnetic waves are really the movement of packets of energy called photons. When matter loses energy, notably when an electron drops down to a lower energy level around an atom, a photon of light is produced. The energy held by a photon relates to the frequency of the light wave's oscillation. The amount of energy carried by a photon is directly proportional to the photon's electromagnetic frequency and, thus equivalently, is inversely proportional to the wavelength. Energy conversion, also known as energy transformation, energian muuntuminen, is the process of changing energy from one form to another. A roller coaster ride is a thrilling exercise in energy conversion. As the chain hauls a roller coaster to the top of the hill, the work done by the motor is transferred to the cars as mechanical potential energy, mekaaninen potentiaalienergia. Mechanical potential energy is energy an object has because of its height or position. This means the higher up or more unbalanced an object is, the greater its gravitational potential energy. Potential energy is stored up somewhere, often by physical effort, to then be released. Once the cars reach the first and highest hill of a roller coaster, gravity takes over. As the car plunges, what it loses in potential energy, it gains in kinetic energy. Pushed upward again by the track, the car reverses that transformation, converting kinetic energy back to the potential energy. In theory, at least, assuming negligible friction and air resistance, the total mechanical energy of the ride remains constant throughout. The coaster comes to a stop with the application of brakes. Brakes apply a friction force to convert the kinetic energy of the cars into thermal energy, which then dissipates into the atmosphere. Every downhill ski racer wants to convert as much potential energy as possible into kinetic energy and, along with it, velocity. That means minimizing the action of external forces. Skiers apply wax to the base of their skis in order to reduce the friction between the ski base and the snow. Alpine skiers wear tight-fitted clothing and assume a crouching arms forward position to minimize air resistance. As the skier reaches the bottom of the slope, nearly all potential energy has been converted to kinetic energy. We need energy to stay alive, grow, keep warm, and be active. Our life is based upon the conversion, utilization, storage, and transfer of energy. Every living cell is a miniature chemical factory powered by energy from chemical reactions. Chemical energy is provided by carbohydrates, fats, and proteins in the food and drinks that we consume. The process of cellular respiration extracts the energy stored in nutrients. Chemical energy is converted to thermal energy, kinetic energy, and other forms of energy. The energy content of food molecules can be traced back to the sun. Plants absorb sunlight and convert it into chemical energy of nutrients through a process called photosynthesis, yhteyttäminen. Production of energy means extraction of energy products in a usable form from natural sources. Renewable energy sources, uusiutuvat energialähteet, are naturally replenished. The sun shines and plants produce biomass through photosynthesis. Biomass like wood and energy crops can be burned directly for heat or converted to renewable liquid and gaseous fuels. The energy from the sun also powers the winds and the water cycle. The kinetic energy of wind or water currents can be converted to rotational mechanical energy in turbines. The rotation of the turbine drives a generator. The generator in turn converts the mechanical energy to electrical energy. Solar energy is created by nuclear fusion that takes place in the sun. Solar panels use sunlight as a source of energy to generate direct current electricity. Geothermal energy can be derived from the Earth's internal heat. It is continuously produced inside the Earth. Due to the geological conditions, the use of geothermal energy in Finland has been quite restricted to the utilization of ground heat with heat pumps. Ground heat is solar energy that's stored in the ground. Non-renewable energy resources, uusiutumattomat energialähteet, cannot be readily replaced by natural means at a pace quick enough to keep up with consumption. Nuclear energy is the energy in the nucleus of an atom. In the process of nuclear fission, atoms are split to release that energy. Energy production heavily relies on fossil fuels obtained from fossilized plants and animals in the form of oil, coal, and natural gas. Fossil fuels are classified as non-renewable because they were formed over millions of years. Using energy always makes it less useful, even though no energy is actually destroyed. The least useful form of energy is low-temperature thermal energy. During the transfer of energy, some energy is always lost as heat.
Now take a moment to self-assess your participation and learning outcomes. Are you able to apply the principles of energy conservation to physical situations? Are you able to identify different forms of energy? Can you identify and describe situations in which energy is converted to other forms of energy? Are you aware of the significance of energy conversions in our daily lives? Are you able to identify and differentiate between renewable and non-renewable sources of energy? Thanks for watching and have a great day.